All right, so we're going to look at some vector calculus stuff. So some of the prior knowledge you're going to need for this is you need to hopefully understand what a vector function is, what differentiation by first principles is, vector addition and unit vectors, and also this idea of the instantaneous rate of change of position being velocity. So a bit of physics, but obviously very mathsy as well. So what we're going to do is we're going to begin by considering some point P. So we have this point P here, and as t increases, P moves. As t increases, P moves. So as t increases, it moves towards the left. Now I'm just going to fill these in anywhere I missed. But just be aware that as t increases, P moves towards the left. Now, that parameter t, what we're going to think of it is time. We're going to think of that parameter t as being time. So as time increases, that particle P is moving towards the left. So you might be wondering to yourself, okay, well, where is it in space? What is the x coordinate and what's the y coordinate? What we're actually going to do is we're going to define a vector function of that point P as it moves. So we'd call that vector function r of t, and it's equal to x of t multiplied by the unit vector I plus y of t multiplied by the unit vector j. Now, let's just break this down a little bit more. X of t means its position, its x position in space is a function of time. And that should make sense. Depending on what time it is, that particle will be in a different x position. And similarly, um, as time is different, its position in space in the y direction will be different based on that time, right? And remember, these I hat and j hat are the component vectors in the x and y direction, respectively. Okay, so what we can actually do is we can define that vector. That's going to be a vector from the origin to that point P, which is the vector r of t. Okay, from there, what we can actually do is we can define some other point that's just a little bit ahead of P in time, and we're going to call that Q. So this, I think you would agree, would be the vector r of t plus h, where we've added some h to that time. So again, it's ahead in time, because remember, as t increases, um, it moves as time increases, the particle's moving towards the left, so Q is always a little bit ahead of P because it's t plus h. Now, as h gets smaller, Q is going to move towards P, I think you would agree, because if h was zero, then they're the same, right? So keep that idea in mind. All right, the next thing we're just going to do is we're going to add a vector from P to Q. And this is where you need to know some vector addition things. Just very briefly, this is r of t plus h. If I was to subtract r of t, that would be a vector pointing sort of in this direction, and then I'd connect them that way to there, which corresponds to this green vector. So this green vector, I think you would agree, is r of t plus h minus r of t. That is this green vector, right? Okay, and what we're going to say to ourselves is, okay, let's think about how we could apply first principles to this. Now, remember, first principles basically says you take the difference in the two functions and then divide by how far apart they're separated, so divide by h, and then you take the limit as h approaches zero. So if you think about it like this is basically the instantaneous rate of change of the position at the point P. So as h gets really small, so we're taking the limit as h goes to zero, this r of t plus h minus r of t, you have to use your imagination a little bit, is going to increasingly point in the direction of being a tangent to the point P. So it's hard to see, but that r of t plus h minus r of t is going to be pointing in that direction as h gets close to zero. And what we can actually do is we can put that on the graph. It's actually going to look like this. That's going to be our vector that's tangent at the point P when h is small, right? Really, really small, approaching zero. And so again, this is the instantaneous rate of change of position. But hopefully you're aware that the rate of change of position is velocity, because velocity is basically how quickly is your position changing. If your position is changing very quickly, then your velocity is large. It's like going from one end of the room to the other end of the room. If you can get there in less time, then your velocity must have been larger, right? So this vector here is our velocity vector. It's pointing in the direction that the particle is moving at that point P. So this point P, as it moves, you'll notice as time passes, that vector is always tangent to the point P because that's the direction that P is moving at each time. So when P is here, the overall direction it's moving is in the direction of this vector here. And that's made up of the two component vectors in the y direction and the x direction. So let me show you those vectors. They're going to look like this. We've got part of the motion of the particle P is moving in the y direction, and part of it is moving in the x direction. And so what we say is this velocity vector is going to be Pythagoras applied to these two components, right? And, just to sort of drive that point home a little bit, if we were to make t come to here, you'll notice that blue vector is going to 0 at the turning point, and that should make sense. Let's think about how the position is changing at that point. At that turning point, the point is neither moving up or down. Its velocity in the y direction is 0. So that's why it's entirely moving towards the left at that point in this case. And then when we get for larger t, when it starts to move down, well, then the velocity is moving in that direction. The y component of the velocity is downwards. And, similarly back here, the y component of the velocity is upwards because the point in the y direction is moving up. You'll notice the pink vector is always moving to the left because that's the direction that the point is moving. It's always moving towards the left. Okay, so that's how we get that. Now, the really interesting thing is, this is the velocity vector. This is the velocity vector, which has, is made up of these two component vectors. In any case, so I suppose we can conclude that if we have some vector function r of t, which is x of t multiplied by I hat plus y of t multiplied by j hat, then to find the derivative of that vector function, it's simply the derivative of the x component, which is a function of t, multiplied by the unit vector I plus the derivative of the y component with respect to t multiplied by the unit vector j. So pretty complex idea, but hopefully that made some sense in terms of what's going on with this vector calculus stuff. Let me know how you're going with all your work, and hopefully you're making some sense of things, and good luck. I'll talk to you soon.